Mini lesson 3C, Characteristics of Polynomials. Describe the following characteristics for each function. On A, we have 5x squared plus 2x plus 7 equals y. We want to find the biggest exponent. That's right here. The leading term is that entire term, 5x squared. The leading coefficient is the number in front of that, which is 5. The degree is 2. That's the biggest exponent. If we were to sketch a graph of this one, it's going to be a U shape. On the left side of this graph, as x approaches negative infinity, y approaches positive infinity. As x approaches from the left side, the y goes up. As x approaches positive infinity on the right side, y also goes up. Let's look at all of the exponents. We have a 2 that's even, we have a 1 that's odd, and then we have a 0 that's even. Even and odd, so we're going to put neither. It's neither an even function nor an odd function, since it has both kinds of exponents. B, negative 5x squared plus 7 equals y. The biggest exponent is 2, so the leading term is negative 5x squared. Leading coefficient is negative 5, and the degree is 2. We're going to have an upside down parabola this time. On the left side and the right side, the y is approaching negative infinity. They're going down on both the left and the right sides. Let's look at the exponents. 2 is an even number. 7 is the same thing as 7x to 0. 0 is also an even number. This is an even function. C, 4x cubed equals y. Our leading term is their only term, 4x cubed. Our leading coefficient is 4, our degree is 3, it's cubic. The graph will look something like this. On the left side, the y is going to be approaching negative infinity. And on the right side, as x approaches positive infinity, the y also approaches positive infinity. Left, down, and right, up. The only exponent here is a 3, which is an odd number. This is an odd function. D, negative 4x cubed minus 8x squared plus 1 equals y. Our leading term has a 3. That's the biggest exponent here. Negative 4x cubed. Now, the leading term might not always be at the very beginning of our equation, only if it's put in standard form already. Our leading coefficient is negative 4 and our degree is 3. Our graph will look something like this. As x approaches negative infinity, the y is going to approach positive infinity. And as x approaches positive infinity, the right side, the y is going to be approaching negative infinity. Left, up, and right, down. The exponents, we have a 3 that's odd, a 2 that's even, and then x0 that's even. We have both, so this is neither an even nor odd function. Identify the real root for each graph. State the smallest possible multiplicity for each real root graph and its factor. The root for this one is at x equals -2. The multiplicity is 1. When we change from zeros to factors, we're going to have x plus 2. If you plugged in -2 for this x, you would get 0. The exponent will be its multiplicity, which is 1. This one, it crosses through the x-axis. The next one, the root is x equals 2. The no multiplicity here is 2. It touches the x-axis. And then the factor would be x minus 2. The multiplicity would be the second one, this 2. On this one, the 2 touches the x-axis. The third one, the root is x equals 2. It has a multiplicity of 3. The factor is x minus 2 to the third power. This one inflects at the x-axis. What is the multiplicity of each factor? X has a multiplicity of 1. X minus 2 has a multiplicity of 6. That's the exponent of that factor. X plus 3 has a multiplicity of 2. And x minus 5 has a multiplicity of 1. The roots for the first one would be x equals 0. For this one, it would be x equals 2. The next one, x equals -3. And x equals 5. You just set the factor equal to 0. On the next page, you have a chart that shows you the 4 different types of end behaviors you can have. If the leading coefficient is positive, you're either going to have up, up if the degree is even, or down, up if the degree is odd. If the lead coefficient is negative, we either have down, down, or up, down, depending on if that degree is an even or an odd number. For the last page, we have even functions, odd functions, and neither even nor odd. For even functions, the output will be the same for the positive input as the same negative input. It's basically algebraically you want to show that f of negative x is equal to f of x. If it is an even function, the graph is symmetric with the y-axis. For odd functions, the output for a negative input will be the same absolute value for the same positive input, except that sign will change. Algebraically, you would show that f of negative x is the same thing as negative f of x. The graph also has symmetry with the origin. Basically, if you were to reflect it across the x and across the y-axis, you would get the same image. You could also say that you rotate it 180 degrees, either clockwise or counterclockwise. Neither even or odd. If neither of those show that they are true, then you would say that it's neither even or odd function. Now, if you have the equation in standard form already, you could just use the exponent trick where you look at the exponents. If they're all even, it's an even function. If they're all odd, odd function. If you have both, you'd put neither. The last part of this page, we have parts of a polynomial. The a1 is a root with a multiplicity of 1. A2 is a touch. It has a root with a multiplicity of 2. A3 is an inflection point. It has a multiplicity of 3. B is the vertices. We have at the bottom an absolute minimum. And then up here towards the middle, we have a relative maximum. And behavior on the left side, right side, looks like it's going up on both sides. D is the decreasing intervals. We have from negative infinity to the absolute minimum for whatever x value that is. And then from the x value of the relative maximum to A2. And then the rest of the graph are increasing intervals. And then F is the y-intercept.